All right, so here's the electromagnetic spectrum. So all that the electromagnetic spectrum is doing is it's showing you all different kinds of electromagnetic waves. Here are some of the waves you are familiar with: AM radio, FM radio. So AM radio is roughly around 1 megahertz. FM radio is around 100 megahertz. Microwaves are around 10 gigahertz, gigahertz to 10 gigahertz. Radars use electromagnetic waves of frequency around 100 gigahertz. Okay. Light, visible light that your eyes are sensitive to has a frequency of 1,000 trillion hertz, 10 to the power of 15 hertz. X-rays are 10 to the power 18 hertz. Okay. So X-rays, X-ray photon is 1,000 times more energetic than a visible photon. Okay. I'm sure you guys have seen this formula. So light comes in photons, and the energy of a photon is Planck's constant times the frequency. Okay. So higher the frequency, higher the energy of the photon. Okay. And since the frequency of X-rays is 1,000 times that of visible light, the energy of an X-ray photon is 1,000 times that of visible light. Okay. X-rays are that, and here are gamma rays, and in principle, there's no limit to the. You can have as high a frequency as you want. Okay. All right, so this is the electromagnetic spectrum. Again, this is arranged in order of higher frequency, higher frequency. The speed of light is constant, which is frequency times wavelength. Higher the frequency, lower the wavelength. And so here's another important fact. Okay, so here's a wave. Here's an electromagnetic wave. Here's the wavelength. Okay. Now this, if you use this wavelength, if you're using this wave to see stuff, the smallest object you can see is roughly of the order of the wavelength. Okay. If an object was this tiny, you cannot see this. Okay. Cannot see this using this wavelength. Of course, you can see anything bigger. So the smallest object you can see is of the size of the wavelength. Okay. So that's what this diagram is showing you. Okay. So if you want to see viruses, you can use visible light microscopes and see viruses. You can't see a water molecule using visible light. What you would have to use is you'd have to use X-rays to see water molecules, so to speak. Okay. And of course, with this light, you can see everything to the left of it. You cannot see anything to the right of it. Okay. So for instance, of course, using radio waves, you cannot see water molecules and so on. Anyway, that's what this is saying. And you, of course, can, using visible light, you can see baseballs and so on. So that's a very important thing to remember. If the wavelength of the probe is lambda, the smallest thing you can see with this probe is roughly the size of the wavelength. Anything smaller you cannot see. So what this, so again, here's the electromagnetic spectrum, and so arranged in order of decreasing wavelength, and you can see that. So okay, what this is showing you is, okay, so if an object is at these temperatures, it's showing you the peak of its radiation curve. Okay, you guys might have seen this electromagnetic spectrum. Okay, let me go to. Okay, so here we go. All right, so you see here is the temperature of various stars. I mean, temperature of an object. No, that's too bad. Okay, so you can see as you warm up the temperature, the peak, so as you warm the temperature of the object, the peak goes to the left. And okay, so our sun has a temperature, surface temperature of roughly 6,000 degree Kelvin. The peak of the intensities is around green light. Okay, so that's what this thing is telling you. If the temperature of various stars, so this is 1,000 Kelvin, the temperature of our sun is roughly 6,000 Kelvin, and that's why it appears yellow. If you had a star whose surface temperature was 10 million degree Kelvin, it would appear blue. You guys have heard of red giants, and those are fairly cool stars. So their surface temperature is roughly the surface temperature of the Earth, or a little more than that. Okay, so that's what this graph is showing you. Okay. So now let's talk briefly about visible light. So like I said, your eyes are sensitive to that narrow band of the electromagnetic spectrum. Okay. And so this is the visible band. These wavelengths correspond to, so we can see from roughly 700 nanometers to 400 nanometers. And again, the lower the wavelength, higher the energy. So violet light has more energy than red light. Okay, so and our eyes are most sensitive to roughly 550 nanometers, so roughly yellow-green light. That's what we're most sensitive to. Okay, so those are the wavelengths we can see. Okay. So we can see from 700 nanometers to 400 nanometers, roughly on the average. We are most sensitive, so this is relative sensitivity to wavelength. Okay, so our eyes are not too sensitive to violet light, and see the sensitivity falls off like so. Okay. And it turns out that you can see 7 million shades. Every wavelength is a different shade. Okay, so it turns out that roughly, so 550 nanometer and 550.01 nanometers, something like that, will appear different shades. Okay, so anyway, so what we can distinguish about 7 million shades. And of course, your computer monitor can render 16 million shades, but anyway, something like that. All right. So let's see how microwaves work. All right, so you saw that a water molecule has a dipole moment. So now so here's the water molecule. I'll draw this water molecule over here. You saw that the oxygen atom is greedy for electrons. So the water molecule, let me do a bigger picture. So here's the Mickey Mouse molecule. The oxygen atom is greedy for electrons. And so here is the dipole moment. Okay. Now what we'll do is, here's an electric field. Here's an electric field. And here's the water molecule. Okay, and there's the dipole moment. Okay, so what this electric field does is it'll turn the dipole moment in this direction. So what this water molecule is doing is it's grabbing hold of what this electric field is doing is it's grabbing hold of the water molecule and turning it this way, turning the water molecule this way. So what it's trying to do is it's trying to orient the water molecule like so. Okay, it's trying to do that. Now let's do the following. Now let's switch the electric field. And now what it'll do is this water molecule, initially it was trying to turn it this way, and now it'll try and turn it that way. All right, so if you have a water molecule, okay, and if you have an electric field that's going back and forth, okay, what it'll do is it will grab hold of this water molecule and it'll jiggle it back and forth like this. Okay, and so this oscillating electric field pumps energy into this water molecule. It heats up this water molecule. Okay, and that's what a microwave does. Okay, so in a microwave, the electric field is oscillating 5 billion times a second. So it's grabbing hold of the water molecule and it's shaking it 5 billion times a second. And all food has water in it, so the microwave heats up the water in food, and then the heated water, hot water, surrounds everything around it. Okay. So interactions between the molecule distributes the energy being pumped into them. Okay. All right, so here's how a radio station works. So here's an oscillator attached to this RLC circuit. So it's pumping energy into this circuit, which is coupled via transformer to this LC circuit, and this is the antenna that's radiating the electromagnetic waves. Okay. So electromagnetic waves are produced by accelerating charges. Okay. The dipole antenna radiates waves of frequency 1 over L square root of LC, which is this is L, and this is attached to a capacitor. So there's the frequency at which this radiates, and so if you want to pump the most energy, so this is LC, most energy, you have to pump it into this frequency. It better match the frequency of this oscillator, all right, which is hooked to this oscillator and radiating energy. Okay. So what you want is a dipole antenna is made of 2 rods. So this is the dipole antenna. Okay. The length of each rod is equal to 1/4 the wavelength of the emitted frequency. So for FM radio, which the frequency is about 100 megahertz, and the rod is about 3 meters long, so 1/4. So each of these rods for FM radios is about 75 centimeters long. Okay. So that's what we're saying here. And of course, if you're an electrical engineer, you can enroll in in antenna theory courses and so on. So you'll learn that kind of stuff over there. So the magnetic field lines are concentric circles around the antenna and so on. Okay. Now you've heard of AM radio and FM radio. Now the difference is the following. Okay. In AM radio, so the carrier signal is the green signal, and the signal that you want to carry is that red signal. Okay. So for instance, in AM radio, when you play a song, the song is converted to an electrical signal, audio is converted to an electrical signal. So there's the audio signal, the red signal, and that is imprinted on the carrier signal. So AM radio means amplitude modulation. And you see, oh, no, I'm sorry. It's the blue signal that's the blue signal is what's being imprinted on the carrier signal. So the blue signal is the audio. And you see the green signal, the carrier signal got modulated, and the red signal is the modulated signal. And that's what's being transmitted. The problem with AM radio is other signals, spurious signals, noise can influence AM radio. Okay. So FM radio gets around that. So AM radio broadcasts in around 1 megahertz. FM radio broadcasts around 100 megahertz. So the way FM radio gets around that is, so again, here is the message that's being sent. Okay, so the blue signal. What they do is, this is the message is a combination of frequencies. So the carrier signal is again the green signal. What FM radio does is it varies the frequency of the carrier signal. Okay. So the red signal is the modulated signal, and it's changing the frequency. And when you do that, now noise, other signals cannot influence the signal. So that's why FM radio, there's no noise there. Okay. That's the advantage. The disadvantage is AM radio can travel much further. FM radio doesn't travel as far. Okay, so it's got to be line of sight. Okay. So you cannot catch an FM radio from New York. Okay, but you could catch an AM radio from New York, because this signal gets bounced off of the ionosphere and stuff like that. Okay. All right, so so FM radio is 100 megahertz. Cell phone use gigahertz signals. Wi-Fi uses higher frequencies than that. Okay. By the way, so you can go to the Wikipedia page of and see AM and FM modulation. Okay, so see FM radio, you can see that the frequency is modulated, and this is the signal that you're trying to transmit. AM radio, it's amplitude modulation, and that's frequency modulation. Okay, so the same signal being transmitted via AM radio and via FM radio. Yeah. So that's what that's. And by the way, so each AM station is assigned a specific carrier frequency that is allowed to vary by plus or minus 5 kilohertz. So AM station is 1 megahertz, so plus or minus 5 kilohertz. You can change. In FM radio transmission, the frequency of each station is about is allowed to use 100 kilohertz. Okay, so let's see. Okay, so what we are saying is, so 90.7 megahertz is a station. Okay, and so 90.7, 100 kilohertz is 0.1 megahertz. Okay, so this station can use up to plus or minus 1 megahertz. Okay, so what we are saying is, the frequency changes that happen, all those frequencies are between 90.7 and 0.1 megahertz. Okay. And so that's why the next station FM radio is 90.9, the next closest station. They have to be separated by 0.2 megahertz. Okay, so that's where those stations come in. All right. By the way, so if you want to use electromagnetic waves to transmit data, higher the frequency of the wave used to carry data, more data can be transmitted. And so now you understand this. So Wi-Fi signal use higher frequencies because more data can be transmitted. Okay. All right, this graph just shows you for a dipole antenna, the intensity of radiation is highest in a plane perpendicular to the dipole antenna. And the intensity of radiation is 0 along the axis of the antenna. So if you hover in a helicopter right above the radio station, you don't get any signal. The signal is most intense in that direction. All right, guys, so that finishes this chapter.